This is for NSV 408, Group 5. We'll be talking about in situ airstripping remediation. This presentation was done by Claire Geyer, Jonathan Hood, Jill Weaver, and Garrett Ziegler. For the first part of this presentation, we'll talk about the physical mechanisms, which describe the principal and crucial physical mechanisms by which the remediation method works. In situ airstripping, it's a remediation technique designed to eliminate volatile organic compounds, or VOCs, and other contaminants from groundwater and soil without the need for excavation. In situ airstripping is particularly suitable for removing volatile contaminants like gasoline, diesel fuel, and chlorinated solvents, and it can be applied in diverse site conditions, often complementing other remediation techniques to achieve comprehensive cleanup of contaminated sites. The process begins with the injection of air or oxygen into the contaminated subsurface environment via wells or other injection points. As the injected air bubbles rise through the groundwater, they come into contact with the contaminants present. Volatile contaminants, which readily vaporize, migrate through the liquid phase, or groundwater, to the gas phase, or the air above, due to the concentration gradient between the two phases. This process, known as mass transfer or volatilization, facilitates the removal of contaminants from the groundwater. Once in the air phase, the contaminants can be captured and treated using various methods, such as activated carbon adsorption or thermal oxidation. Throughout this operation, continuous monitoring is conducted to assess the effectiveness of air stripping processes and to optimize the system for improved efficiency. In situ air stripping is particularly suitable for removing volatile contaminants like gasoline, diesel fuel, and chlorinated solvents, and it can be applied in diverse site conditions, often complementing other remediation techniques to achieve comprehensive cleanup. This is a visualization of what occurs where air is injected through wells, and as the contaminants volatilize, vapor extraction is used to remove. This example uses some kind of canister in the ground, which probably holds a fuel and shows contamination. Volatilization is a physical process where substances transition from a liquid or solid phase to a gaseous phase. It occurs at the surface of the subsurface where molecules gain enough kinetic energy to escape into the air. For example, a puddle of gasoline on the ground, as the temperature rises, molecules of gasoline near the surface of the puddle gain energy and become increasingly agitated. Eventually, molecules break free from the liquid surface and enter into the air as vapor. The process continues until an equilibrium is reached between the rate of molecules evaporating and the rate of molecules condensing back into the liquid phase. In the context of in situ air stripping or air sparging, volatilization occurs when volatile contaminants in the groundwater or soil transfer from the liquid or solid phase to the gas phase as air or oxygen is introduced into the subsurface environment. In situ air stripping can enhance biodegradation of contaminants in groundwater and soil by enriching the subsurface environment with oxygen. By injecting air or oxygen into the contaminated zone, this technique increases the availability of oxygen, crucial for aerobic biodegradation processes. Oxidated conditions foster the growth and activities for aerobic microorganisms, which naturally degrade organic contaminants. These microorganisms metabolize the contaminants, breaking them down into simpler, less harmful compounds. The accelerated microbial activity, coupled with enhanced oxygen supply, leads to a quicker and more efficient degradation of contaminants. Ultimately, in situ air stripping promotes the remediation process by creating an environment conducive to aerobic biodegradation, thus facilitating the removal of pollutants from the affected site.
This video is a visual representation of how in situ airstripping works. There are influencing factors on the air stripping system, such as geological and contaminant characteristics, that have a big impact on the system's efficiency and effectiveness. A few pros of using the remediation method of air stripping include cost efficiency and a high reliability and efficiency of removing volatile organic compounds commonly known as VOCs. The cons of using this process include the potential of spreading pollution instead of remediating the soil in the case where the conditions of the medium are not ideal, such as being saturated with liquid. Another con to using this process is that the air stripper system is site-specific for certain contaminants. The last con is that air stripping is only effective for the removal and remediation of volatile organic compounds due to their high volatility, which is their ability to change into a vapor. This means that other contaminants that are not organic or not volatile, like metals, will not be removed using this process. Geological conditions have a large impact on the effectiveness and efficiency of in situ air stripping. For water-saturated porous media, studies have shown that when air is injected into a saturated media, it can only move where there is no water and will therefore only move in discrete channels. This will not allow the air to pass through the entirety of the porous media as bubbles and therefore lowers the effectiveness of air stripping. Other geological conditions like low permeability also have negative effects on the air stripper's process. The presence of a low permeable zone overlaying the target zone prevents capture of the volatile organic compounds in the soil venting system. In this case, the air stripping could be causing potential spreading of the contaminant as the VOCs are not being contained properly. With more exposure of the contaminants to the air, the better the process will work. The air that is being injected into the water is what causes the contaminants to become vapors. This means that the more air that can be injected into the water, the more efficient the system will be at removing the contaminants with the injected vacuum wells. Henry's law constant is the primary indicator of a chemical's potential for removal. This is because this constant explains how easily a contaminant will vaporize. If it is larger, it is more readily vaporized than a contaminant with a lower constant. The constant is the ratio of the concentration of a dissolved gas in a liquid to the partial pressure of that gas when the gas is in equilibrium with the liquid. Air stripping also works better for more volatile components. In fact, the bigger the Henry's constant and the more volatile the compound, the better air stripping will work for the contaminant. Air stripping has also been found to not work for metals or inorganic compounds, as these substances will not vaporize readily when in contact with air or oxygen. These substances will have low Henry's constants. The next topic is field implementation of the air stripper system. The first step of implementation of the air stripper in the field is the installation of the wells, the air sparging and vapor extraction wells. The wells are an integral part of the treatment system because it is what makes the system in situ. Air is injected into the ground in the contaminated water source, making the volatile organic compounds vaporize, therefore leading them to be extracted by a vacuum, which is the vapor extraction well. This is located in the porous medium, in other words, the soil that lies above the contaminated source. This well vacuums up the vaporized VOCs and takes them to the treatment system that is above the ground. The next step is implementing the air injection system. The injected air that will encounter the VOCs comes from this component. There must be an air source that can produce enough pressure that the air reaches the water and can create many bubbles, so that the air will then touch the contaminants and cause them to vaporize. Before, we learned that the more bubbles that can be utilized, the better the overall efficiency of the air stripping process will be. The third step of the system is the vacuum pump that is connected to the vapor extraction well, or the vacuum. This part of the system removes the vaporized VOCs from the ground and transfers them from the pores of the soil to the above-ground treatment system. The above-ground treatment system is not part of the in-situ air stripping process. However, it is still important to understand a few of the possibilities that can be utilized to treat the trapped VOCs. The three options listed here are biofiltration, adsorption with activated carbon, and catalytic combustion. The treatment system is considered step 4 in this instance. The first choice is biofiltration, which is sub-step 1 of step 4. The method of biofiltration uses bacteria or other organic matter to neutralize pollutants, such as volatile organic compounds, that are present in contaminated air or water. For example, a slime layer where bacteria will fester and thrive is grown using porous media. Periodically, the tainted water is trickled over this layer of slime bacteria, enabling the bacteria to absorb the dissolved organic material on this medium. Sub-step 2 of step 4 is the second alternative, which is adsorption using activated carbon. This method uses the pores of the activated carbon to attract and trap the pollutants that are either liquid or vaporized. It works well to remove pollutants from large amounts of water or air that have low concentration. It works well to remove odor and color, but is not effective for non-organic substances. Sub-step 3 of step 4 is the third alternative, which is catalytic combustion. This process includes mixtures of fuel and air that are passed over a catalyst maintained at a temperature high enough to favor total oxidation of the VOCs.
In situ airstripping has been extensively used to remediate sites contaminated with petroleum hydrocarbons such as gasoline, diesel, and jet fuel. These contaminants are often present in subsurface environments due to leaks from underground storage tanks or industrial activities. By injecting air or oxygen into the contaminated zone, in situ airstripping enhances the volatilization of petroleum hydrocarbons, allowing for their removal from groundwater and soil. This method is also effective for treating sites contaminated with chlorinated solvents like TCE and PCE. These solvents are common industrial pollutants that can persist in groundwater for extended periods, posing risks to human health and the environment. In situ airstripping promotes the volatilization of chlorinated solvents, facilitating their removal from the subsurface and reducing the potential for further contamination. In situ airstripping, or beyond petroleum hydrocarbons and chlorinated solvents, in situ airstripping is applicable to a wide range of volatile organic compounds, or VOCs, found in contaminated sites. These may include industrial chemicals, solvents, and byproducts of various manufacturing processes. By introducing air into the subsurface, in situ airstripping promotes the transfer of VOCs from groundwater or soil to the vapor phase, allowing for their capture and treatment. In situ airstripping has been utilized in the remediation of landfill sites contaminated with organic compounds, leachate, and other pollutants. By injecting air into the landfill substrate, this technique accelerates the degradation of organic contaminants and reduces the leaching of pollutants into surrounding groundwater. In situ airstripping remediation technologies offer versatile solutions for addressing a wide range of contamination scenarios in groundwater and soil. Their field applications have proven successful in mitigating environmental risks, restoring contaminated sites, and promoting sustainable land use practices.
For our first case study, we decided to look into the Savannah River site in Aiken, South Carolina. This site was used by the United States Department of Energy to produce nuclear chemicals. This site had a lot of TCE and PCE contamination. The maximum concentration level for TCE and PCE in the United States is 5 micrograms per liter. Before the in situ airstripping used at this location, the TCE had a concentration of between 500 and 1800 micrograms per liter, and the PCE concentration for this site ranged between 85 and 184 micrograms per liter. So this site was really bad. Both of the PCE and TCE had limits way above what the legal limit was. This project was successful and led to the final TCE concentration in the groundwater ranging from between 10 to 1,031 micrograms per liter, and the final PCE concentration in the groundwater ranged from 3 to 124 micrograms per liter. This was significantly smaller than the original concentrations of PCE and TCE, so that's how you know that this site was successful. Also shown on this slide is the layout of the site, with the A areas being the administrative areas and the M area being the more important one, with it being the manufacturing area. It was in this location that they did aluminum forming and metal finishing, which led to the creation of the contaminants in the water. This site used air sparging to complete the in situ airstripping. This was accomplished by drilling 2 vertical wells into the watershed. The one on the left was the injection well, which was used to inject air into the ground to remove the VOCs, and the extraction well on the right, which was also drilled to pull the VOCs from below the ground. The injection well was also used to drill a horizontal well across the bottom of the watershed so air sparging could be possible. The air sparging was also used to eliminate the need for surface groundwater treatment, which is why it's in situ airstripping instead of just airstripping. This process in this case led to almost 16,000 pounds of VOC being removed from the site in 139 days. This site also ran numerous tests and monitoring measurements. They frequently monitored the pressure of the Vados zone piezometers and the injection well. They monitored the vacuum gauge at both the extraction well and the surface. They used a temperature gauge to measure the temperature at the Vados zone piezometer, the injection well, and the extraction well. Also, more importantly, they ran a biweekly microbiological sample on well clusters that were attached to the wall of the wells. Vapor sampling was also another very important test that they ran on the site. They ran it on the Vados zone piezometer, the extraction well, and the bundle tube. All of the sediment samples, the first 2 that I mentioned, were taken at 5-foot intervals along the Savannah River. The microbacterial samples were taken in 10-foot intervals, and the vapor grab samples were analyzed using a photovac field gas chromatograph. This site was a little more expensive than the other case study we're going to look at, but overall it cost $412,286 to create and run this site for a year. $253,525 of this total went into the creation of the site. The site cost setup was $5,000, and that was just to level the area for where the wells are going to be built at. It cost around $170,000 for the well installation. This price included the cost to design and engineer the wells as well as moving and installing the wells into the actual site. The remaining about $80,000 was used for equipment. This includes an air injection system with a 300 cubic feet per meter blower, an air extraction system with a 600 cubic feet per meter blower, a vapor air separator, a carbon absorption unit, a duct heater, a water treatment unit, monitoring equipment, temporary storage, a portable generator, fuel storage, piping, and installation. The other $159,000 was used through labor and consumables. This site used 3 technicians, 2 laborers, 2 oversight engineers, and a maintenance and monitoring crew. And then consumable-wise, they used carbon recharge, diesel oil, lubricants, deionized water, chemical additives, and maintenance supplies. The next one we are going to look at is the La Crosse town in La Crosse, Kansas. This site had different contaminants from the other one. It had MTB, which was the most important one because of how potent it was, BTEX and TPH into their drinking water. The biggest problem at this site was the extreme amounts of MTB, like I just said. The site became polluted from leaking underground storage tanks at 3 gas stations located about a mile away from the treatment plant. The state of Kansas opened a permanent air stripping system in 1997 to treat the MTBE and other pollutants. This system's still in place now. The system had a design flow rate of 480 gallons per minute, and MTBE also had an influent concentration of up to 1,000 micrograms per liter. The air stripping system used was a 2-tower system, much like the other one we just talked about. The first tower was designed to remove the MTBE to levels below 10 micrograms per liter, and the second tower was used to polish the water after the fact. The influent water was softened with lime, and then it was set into a settling basement for flocculation. From this basement, it was pumped through a sand and anthracite filter into a $200,000 gallon underground well. The site used both a temporary shallow tray stripper and a permanent pack stripping tower system. The temporary shallow tray stripper was put in place in the meantime until the permanent pack stripping towers could be installed. The 5-tray air stripping system was in operation for 5 months before the permanent system could come online. The system was able to reduce MTBE levels from 200 to 600 micrograms per liter to 17 to 375 micrograms per liter, which was good, but it wasn't as efficient as they were looking to be, so they put in this new system. The new system is currently still in operation, and it was able to consistently hit a concentration of 10 micrograms per liter, which is the US required amount. The concentration was below 0.2 micrograms per liter detection 30% of the time, and then throughout their testing for 2 years, they took 69 samples, with 64 of them being below the cleanup goal. The 5 samples that were not ranged between 19 and 74 micrograms per liter, and we're going to get into that in a second. So here is the visual to go with the information from the last slide. It shows all of the tests run between September of 1977 and September of 1979. At the bottom of the chart, you can see both the concentration for the effluent and the tap water of the system. For the most part, both these values stay consistently below the allowed 10 micrograms per liter requirement. These values only really spiked when the influence spiked, and they ran additional testing and found out it's because they used primary well 5 for the majority of the time, and then on weekends they swapped to primary well 6 as a backup just to give well 5 a break. And they found that in this well 6 that there was a higher increase of all the chemicals that they were trying to get rid of, which led to the higher results after removal. And they decided to decrease from taking 20 hours of water a week from this well to about 4 or 5 to help avoid this problem. And then lastly, for the cost and the results, the total capital cost of this project was $185,000. There was also an operation and maintenance cost of about $30,000 annually. After the first 2 years of operation, there were no exceedances in the cleanup goal. The first stripper on average removed 83% of the pollutants, and the second stripper on average removed 95% of the remaining pollutants. This gave them about an average of 92% reduction of the pollutants in the tap of the well.
Moving on, we will now expand on the different advantages that air stripping has over other methods of remediation, as well as the disadvantages that come with using this technique. One advantage of in situ air stripping is that the technology used to conduct this process is readily available. Components such as air compressors and pumps are used for a number of different applications and are easy to come by. Another big advantage is that it causes very minimal disturbance to the surface and any ongoing operations taking place. Just like most in situ methods, this method is a good choice of remediation if it is taking place in an area where we don't want major disruptions to the ground. Also, air stripping has relatively short treatment times, with the average treatment taking less than 1 to 3 years if performed under optimal conditions. Additionally, this form of air stripping is less costly than operations that require removal of groundwater for treatment. This is more generally an advantage to most, though not all, in situ methods, and will be discussed further in the cost analysis later in this presentation. The last way in which this method is useful is that it can increase the amount of contaminant removal when combined with soil vapor extraction, also known as SVE. To expand, combining air sparging with soil vapor extraction allows for a greater extraction of vapor from the ground, both above and below the water table. SVE, when used as an in situ method, works by creating a vacuum effect on the aquifer. This oftentimes relies on the surrounding area being covered or paved over in order to work, which could be seen as a disruption to the local environment. This is one disadvantage to using air stripping in tandem with SVE, though the additional efficiency may make the added technology worth the extra work that needs to be performed. Once the vacuum is created,
It pulls gas from above the water table and into a treatment system. The vapor is run through a water-air separator. This removes excess moisture, which can interfere with the treatment process. The harmful vapors are then separated from the rest of the air via filters, commonly made from activated carbon, though also occasionally biological components that are able to break down the specific vapors created. Those performing the remediation will have to decide based on their particular project if SVE is best for their intended goals or if it will cause a disturbance to other surface operations. On the other hand, there are also several conditions that make airstripping a less than ideal method. One of the biggest problems with this practice is that it cannot be used in situations where there is free product. This is due to the fact that air sparging can cause a phenomenon known as groundwater mounding, which can cause free product to travel, moving contaminants further away from the source. Another issue that can arise with air sparging is that it cannot be performed to get rid of contamination in confined aquifers. In confined aquifers, the vapor becomes trapped below the confining layer and cannot rise to be released or treated. Air sparging may also prove to be ineffective in stratified soils, meaning the soil's porosity changes at different depths. This method works best with a consistent permeability to ensure both the efficiency of the contaminant's reaction with the air and to ensure that the resulting vapor can rise above the saturated layer. Additionally, there are some interactions between the chemical, physical, and biological aspects of the procedure that are not well understood. In order to determine the feasibility of air stripping, we need to know a number of different characteristics about the soil and pollutants, as well as the ways they affect one another. Depending on the specific site's characteristics, additional research may need to be conducted before sparging can be implemented. Another downside that should be carefully considered is the application's potential to cause the spread of contaminants. When performed under certain conditions, air stripping can push vapor and liquid constituents away from the source. In order to prevent this and to ensure that the treatment is working properly, the system should be very carefully monitored. Pilot testing should also be used to demonstrate how air moves through the soil before the real stripping is performed. Finally, we will move on to the last considerations for air stripping. It is important to take note of whether or not there are any basements, sewers, or other underground closed-off spaces in the area. If these places exist, they will either need to be properly vented or another method of remediation will need to be considered for the spill. This is due to the fact that pollutant vapors can build up in these spaces at levels dangerous to human health. The existence of these underground structures will incur additional costs that we should consider should we decide to move ahead with air sparging. Also, as mentioned earlier in our presentation, many characteristics of the soil and other constituents are contributing factors to the efficiency of air stripping. To simplify this idea, this method is generally most effective when attempting to move kerosene, gasoline, and other chemically similar materials from the soil. This is due to their high vapor partitioning, which allows them to enter a gaseous state more easily than some other pollutants. The soils that will perform best under this method are loose soils with high permeability, such as sands and gravels. This type of soil allows air to travel more freely and rapidly to the surface. As previously mentioned, a discussion of the cost of this type of system is needed to determine if it is viable. There are a few different aspects of treatment that influence the cost of the overall project. These include the total surface area of the contamination, the depth beneath the surface to which the contaminants have sunk, the potential difficulties of removal dependent on the type of soil, and any additional technologies that may need to be used on site. Additional technologies could include the previously mentioned ventilation systems, which would need to be put in place if there are underground structures in the area or the equipment required for soil vapor extraction. The level of automation refers to how much of the process can be done without needing oversight or operation by an employee. Greater amounts of operation can give way to higher capital costs, but lower operating costs since a salary does not need to be paid. The following image shows a cost analysis performed by the Federal Remediation Technologies Roundtable, or FRTR. The FRTR was established in 1990 to bring together different government agencies to collaborate with the goal of hazardous waste site remediation. The roundtable describes the average cost of air sparging for different sizes of spills and different difficulties of treatment. As you can see, the difficult spills have a sand silt or sand clay soil type and are located deeper underground. All aspects other than this difficulty and the size are kept consistent in order to provide a reasonable comparison. All costs are averaged based on the scenarios that best fit the described criteria. Continuing with this analysis, the table also takes into consideration the operating and maintenance costs for this project. It considers the small area spills to operate for 2 years, while the larger projects are considered to operate for 5 years. There is also an additional cost considered for design, which is naturally the highest for the most difficult and largest remediation site. After adding together all of these costs, we can see that the highest cost once again is for the biggest site with the greater challenges, while the cheapest cost is designated for the smallest site with loose soil and a shallower depth to contamination. Once the total marked up costs are determined, they can then be divided by the volume of pollutant to provide a cost per unit volume analysis. One outlier in this information is that the smaller but more difficult to treat site is cheaper per unit volume than its easier to treat counterpart. In this case, the quantity of air sparge points provides a more efficient treatment. This means that while the overall cost is greater, the cost per unit volume of contaminant will be cheaper overall in spite of the harsher conditions. All values were determined for the table in the year 2000, so in order to have a better understanding of what these values are in 2024, the values were converted to their modern day cost equivalents. As for added costs, we may also consider the price of the previously mentioned soil vapor extraction method. A study performed in 2022 by the EPA illustrated the capital, operating, and sampling costs for a typical application of SVE, once again creating an average from existing sites. From this, an average cost for small and large sites based on the criteria discussed in the cost analysis can be calculated. The cost of SVE is significant when compared to the cost of treatment with air sparging alone, showing the importance of pilot testing to determine if this additional method is needed. This concludes our presentation. Thank you for watching.